Hello, my dear students. Now, this is our first part with the Fourier transform and frequency analysis lecture for the Introduction to Communication course 20ELEC09I. Now, please let me share my presentation and start continuing our fourth part in this lecture. Okay, my dear student, I believe that now you can see my PowerPoint slide, and now this is our first part, as I mentioned, with the Fourier transform and frequency domain analysis. And let me now start running my laser pointer and let's go. Okay, briefly, what we did in the first three parts, we define what is frequency. We define frequency as the number of repetitions per unit time, which is 1 second. Consequently, we discuss the monotone signal, which is a sinusoidal signal, as this signal contain a delta derived impulse in the frequency domain, or what's called the frequency spectrum. And then we discuss what if we have a signal with the summation of two sinusoidal signals, and basically the Fourier transform will be the same, the summation. We also test the sense of the frequency when we hear different voices or different monotones with different sinusoids. Accordingly, we reach what's called the Fourier series theorem, where we conclude that for any periodic signal, it's mainly a series of harmonics of sinusoidal signals, so that we can easily expect the Fourier transform or the frequency spectrum of any periodic signal as a series of a delta Dirac function exists on the fundamental and the harmonic frequencies of the periodic signal. After that, we ask the question, what about the aperiodic signal? And we reach what's called the Fourier transform, where we can use in order to transfer any time domain aperiodic signal into a frequency domain. And also we have what's called the inverse Fourier transform, where we can transfer a frequency domain signal back to the time domain signal. We did an example, a very important example related to the rect function, where we concluded that the rect function will result with what's called a sinc function. And we have a lot of investigation about what is sinc, how we plot this sinc function, and all these stuff. And then we deal, or we discuss together what's called the negative frequency. We agree that there is no physical meaning for the negative frequency. It's just something for mathematical representation and for the analogy and the symmetry of the Fourier transform theorem. And then I turn a question to your side. What if the Fourier transform, what if, sorry, the time domain signal is a sinc function? What would be the frequency domain signal? I believe that some of you have already answered this question and sent me their answers. Of course, I appreciate this effort. And now this is different examples for different signals from the time domain to the frequency domain. This is simply what we have done for the first three parts. Now we are with part number not part number 4, where we are going to deal with what's called the Fourier properties and the frequency domain system analysis. So here, what's called the Fourier properties. Here are some Fourier transform properties related to the signals between the time and the frequency domain. As you can see, some of these properties are very obvious, it's very logic. For example, when you have two signals added in the time domain, then the frequency is simply added in the frequency domain. Actually, we did it. If you remember here, let me return back. Yes, here, exactly. Here is an example for a Fourier transform property. Here, simply, when you are going to plot this frequency spectrum, you would logically transfer the frequency transform or the Fourier transform for the first one and the second one, and then you simply add these two signals together. So this is simply the concept of Fourier series, for example. So this is one of the Fourier transform properties, which is how we can deal with two added signals. Here another one for for example, when your time domain signal is multiplied by a constant, or here when there is some sort of shift, and here for the differentiation and the integration, a lot of properties. Actually, maybe during the tutorial, during the extra hours, we will deal with different properties. But here I will be very specific. I will be to the point. I will give all these, all the remaining portion of the lecture in one single property, which is what's called the convolution property. Because this is one of the main major properties affecting our systems. Please don't forget that we are learning Fourier transform and Fourier series in order to deal with the communication system. So this is our final target. And here we are building the needed background in order to reach this target. That's why I will be directed to the convolutional or the convolution form of the Fourier transform property. So let me first start with the question: what is a convolution? It's a very important question. Actually, we have to answer it first. So now I believe it's better to return back to our simple whiteboard in order to do more about what is convolution. Okay, very simple. Just to remember, I believe you already studied the convolution while you were enrolled in your signal systems classes 1 semester. So, for example, if I told you that we have a signal called g of t, sorry, just to make it online, it's perfect. And this g of t is the convolution of two signals, which are the f of t. Let me use this as the sign for the convolution, and the signal h of t. Okay, perfect. Then, based on your last semester or previous semester classes, you know that this g of t is equals to integration from negative infinity to infinity for what's called f of tau h of t minus tau d tau. Please remember what we already have made when we were dealing with the integration in the Fourier transform, and I told you that please remember that this tau is called what's called a dummy integral variable, because by the end of the day, no tau will appear. It's only a function of t. Tau will disappear. So this is tau is a dummy variable. You can call it x and whatever it is. It's just a dummy variable. Okay, now the question is, what if I told you I need to have a Fourier transform to get what's called a g of omega, where g of omega is simply the Fourier transform for the function g of t. So now what I'm targeting to is to make some sort of Fourier transform to this g of t signal to get what's called g of omega. Knowing that the g of t is the convolution of f of t and h of t, as you can see here. So what will happen? Now let's start to answer this question. Very simple. Let's turn back to the standard relation for the Fourier transform, saying that, let me write it first in the terms of x, which is x of omega equals to integration from negative infinity to infinity for the x of t e power minus j omega t dt. Very simple. This is the relation we use, if you remember, in part number 2, while we were dealing with the rect-to-sinc transformation. So, very simple, we can say that g of omega is the integration from negative infinity to infinity for this g of t e power minus j omega t dt. Very simple again. Just I use g of t and then I get g of omega. But please don't forget that this g of t is a convolution between two functions, f of t and h of t. So now we have to substitute with g of t by its integral form. So let's do it. Okay, so let me write it again. What we reached is as follows. We say that g of omega equals to the integration from negative infinity to infinity for g of t e power minus j omega t dt. And again, we say that g of t, g of omega equals to integration from negative infinity to infinity. Again, e power minus j omega t dt. And what about g of t? G of t is another integration from negative infinity to infinity of f of tau h of t minus tau d tau. So this component, which is the integration from negative infinity to infinity, f of tau, h of t minus tau, d tau, is considered as the convolution due to f of t tau, f of t and h of t, which is simply g. Now we have to make what's called a separation of variables. So we have some components which is function only in tau, like f of tau. And we have other components which are function in t and tau, like here and there. But before proceeding, let's do a very simple mathematical trick, which is as follows. What if we say e power minus j omega t, okay, which is this exponential component, is equals to e power minus j omega t minus tau plus tau. Simply, as you can see, it's the same. I add and subtract the same element tau. Nothing has been changed. So simply this is equal to. Then we can say e power minus j omega t equals e power minus j omega t minus tau times e power minus j omega tau. What I did simply is that I divide this bracket into two brackets. This is t minus tau here, and this tau with the minus sign will become e power minus j omega. Very simple. So what I can make now is that I can substitute this e power minus j omega t with e power minus j omega t minus tau multiplied by e power minus j omega tau. As you can see here, very simple. So the next step is that we are going to replace this e power minus j omega t with these two terms. So let's write again our integral form. G of omega equals integration from negative infinity to infinity, another integration from negative infinity to infinity, and then we have the first is f of tau, h of t minus tau, and then the e power minus j omega t will be replaced by e power minus j omega t minus tau, e power minus j omega tau dt d tau, as you can see here. So in this integral form, what we are going to do is very simple. We can now make what's called the separation of variables. First, let's start with those related to tau, only tau. We have f of tau e power minus j omega tau d tau. So let's write it. F of tau e power minus j omega tau d tau. And then we have another integration from negative infinity to infinity all these terms are multiplied together, which is h of t minus tau e power minus j omega t minus tau dt. These two integrals, as you can see, are multiplied together. Just what I just made is that I rearrange the parameters so that I start with all the tau parameters, then all the t minus tau parameters, just rearrangement for the equation, no, nothing more. So now let me introduce a new dummy variable, which I will call it, for example, t dash. And I will say that t dash is equal to t minus tau. Then t dash is simply equal to t dt. As for this integration, tau is considered a constant. It's an integration only with respect to t. So tau is a constant. So this is the answer. So what I will going to do now is that I replace ht minus tau with t dash. And I will replace delta t with delta t dash. And let's see what will happen. So now g omega equals negative infinity to infinity f of tau e power minus j omega tau d tau multiplied by negative infinity to infinity h of t dash e power minus j omega t dash t d dash. Now, please start to observe these two integrals. Please start to compare with this one. It's a signal or a function with t e power minus j omega t dt. As I said in my second part, and as I said now, this t can be replaced by tau, t dash, x, y, z, whatever. It's a dummy variable. So this integral form is simply represent the Fourier transform for the function. So by observing these two functions, you can say that this term with the integral, of course, represents the Fourier transform for the f signal. So this is f of omega multiplied by this form represents the Fourier transform for the h signal. So it's h of omega. So what we have concluded is whenever you have g of t equals to the convolution of two signal f of t convoluted with h of t, this will automatically transfer in the frequency domain function into a multiplication process. And now you can understand why convolution is important. Because simply convolution is a reverse process for multiplication. When you have a multiplication in the frequency domain, you will have a convolution in the time domain. And for those who have answered the question, the bonus question related to the think to rect function, they can know that the Fourier transform of a sinc function in the time domain is a rect function in the frequency domain. So the Fourier transform is a bidirectional process. I mean, whenever you have a convolution in the frequency domain, this will turn to a multiplication in the time domain. So simply the convolution is the reflection of the multiplication in the other domain. If you have a multiplication in the time, you will have a convolution in the frequency. If you have a convolution in the time, you will have a multiplication in the frequency. Very simple like that. So that's why, my dear student, the convolution is a very important operation for our signal systems and communication courses. So Let me now return back to my slides. Okay, and then let's start, or let's rethink about the conclusion. Now, this is the derivation I just made together with you, and then this is the conclusion. Convolution in a spatial domain equals to multiplication in the frequency domain, and vice versa. Here, we use the word spatial all the time. Maybe I would consider the word spatial maybe in the end of the presentation, sorry, the end of the lecture, but let's call the spatial into the time for our prospective booths are the same, spatial or the time. So now, again, we reach a conclusion that whenever you have a convolutional time domain, it's a multiplication in the frequency domain and vice versa. But again, to what extent this is important for our communication courses? Why we should consider this information as an important information? So let's now turn to deal with systems rather than signals. What I mean by system is simply something like that. For example, you have an input signal, you have a system, and you have an output signal. This is what's called a system. So maybe you hear about the LTI systems or signal systems. We will not go deeply to it, but let's do this very simple circuit example. Let's turn back 2 years ago. When you were in your first year and when you enter the circuit classes, I believe that especially in your end of the first semester or maybe in your second semester with year one, you have already deal with those circuits related to the RLC circuits, I mean resistance capacitance circuits. It's an easy example that you can easily solve. So let's turn now again to our a simple whiteboard and start to solve this very simple circuit. So where is the question? It's a very easy question. You have an R, and this is C, and this is input X, and this is the output Y. And what I'm seeking now for is very simply that I need to have a relation between X and Y, the input and the output. Very simple. I believe you can make it in very easy manner. So you know that this capacitance is represented as an impedance element with the term 1 over J omega C. Maybe you remember this simple information. So whenever we are now going to deal with this signal, we are going to make it very simple. It's a very simple voltage division circuit. So the voltage drop here, which is Y, equals to 1 over J omega C, the impedance in the voltage drop resistance, over R plus 1 over J omega C. Very simple like that. So times X. So now the relation Y over X represents the system. This relation between the output and the input. So we will call this H, or the system response, which is Y over X. To make this equation somehow easy, I will just multiply with J omega C for the numerator and denominator. So I will have a very simple function H equals to 1 over 1 plus J omega RC. Very simple like that. Very, very easy to be recognized. Now, let me ask a very important question. What is H? Is H a time-dependent function? I mean, does H depends on time? Let's start to see. Does H depends on time? The answer simply is no. H does not depend on time. What is the independent parameter for H? If you recognize it right, The independent parameter of h is omega. So this h is simply h of omega. Sometimes actually we rewrite it in this way, 1 over RC over 1 over RC plus J omega. This is just to make the amplitude here is equal to 1 over RC and make it in this manner. Of course, both are the same, but the question here now is this is not a time-dependent response. It's a frequency-dependent response. And we call this very important function as the system frequency response. So what is the system frequency response? It is simply the relation between the output and the input in the frequency domain. Can I have a system time response? Simple answer is yes. Now you can make a very simple, a very easy, simple time response if you use what's called the inverse Fourier transform, and then you will return this h of omega to be h of t, which is the system time response. So now this is the system time response and this is the frequency time. What is important is the following. Let's now return back to our slides. Okay, that's perfect. So this is our system. We did some analysis as I did the x and y, and then we reach this h of omega signal. This is the frequency response of the system. And now, if we make a Fourier transform, we can have the time response of the system. So we have a frequency response of the system, and we have a time response of the system. And then I will plot it later on, but let's now go to this slide, which is a very important slide. Here you can see y of omega equals to h of omega times x of omega. This is simply what I did while I make you the proof for h of omega. I say that h equals y over x. And now h capital is a frequency domain signal. So this is a full equation in the frequency domain. Now, what if you would like to write this equation in the time domain? Then you are going to say that the y of t is equal to the convolution of the h of t and y and x of t. Now the convolution starts to appear because simply this is the reverse process for the multiplication. The multiplication happens in the frequency domain is or will be reflected to a convolution in the time domain. And this is a very important system parameter. And actually, this very important slide comes up with very two important observations. This slide actually answers a very important two questions. The first is, why frequency domain is important? The second is, why convolution is important? The answer is very simple. Now, frequency domain is important because whenever you are dealing with a system, you are dealing with a system in a frequency domain. The multiplication process is in a frequency domain, not in the time domain. So it's usually easy to deal with systems in frequency domain rather to deal with the systems in the time domain. Because as you know, the convolution process is much more complicated with comparison with the multiplication process. And why convolution is important? Because simply this is a reflection in the other domain. Whenever you are doing a frequency domain analysis in a form of a multiplication, on the other side, this is simply a convolution in the time domain. So to make life easy, we are going now to try to plot what we have reached to know how to plot a frequency domain complex signal, which is this signal. We are going now, we will try to make a plot for this signal. And then we are going also to make a very interesting example with this, with this HT and XT signal, which is a very, again, important example. As I usually said, we are not just doing examples in order to make you trained on mathematical operations. This is, of course, one reason, but the main reason is that such examples usually include a lot of observations and closure, as we did with the sync and rect function, maybe in the part number 2 of the first lecture. Now we are going to make another important example with this rect function again and with this HFT signal. So now let's start with this equation. We are now interested to plot this equation. Okay, so what I'm going to do again is to stop sharing and return back to my whiteboard. Okay, so the signal is as follows. We have the signal h of omega equals to 1 over RC over 1 over RC plus. This is the frequency response of the system we have. We are going, or we are trying to plot this signal. The main issue is that this is a complex signal. It's not a real signal, or it's a complex signal. It has a very important emerging point. And in order to make a plot for any complex signal, you have to plot it in the form of a magnitude and phase. You remember this from your mathematics classes. So in order to plot this signal, we have to have a real, an absolute term and an angle. How we can get the absolute? Absolute is actually very easy if you remember this h of omega as an absolute is equals to for the denominator we don't have a problem. It's a pure real denominator. So as you can see, this is such a simple denominator. And for the denominator, it have real part and imaginary part. So the absolute is simply the square root of the real part square plus the imaginary part square. This is the absolute for the signal, or for the h of omega signal. A very simple mathematical equation. Now we are interested in plotting this absolute signal in terms of omega. Again, please remember that omega is considered as your independent parameter. So what are you going now to do is you are interested to plot omega versus absolute h of omega. So let's start with when omega is equals to 0, this origin value. So when omega is equal to 0, it's simply 1 over RC over 1 over RC. So you have a 1. When omega tends to infinity, so this function will be 1 over infinity. So at infinity, this function will tend to 0. So it's somehow a decreasing function. And if you go to any sort of MATLAB maybe, or Excel, or any something like that, and you start to plot it, you will get some function like that. Okay. Before going to the angular, because I see that for a complex signal, we have a magnitude and the phase. Now, this is the magnitude, the absolute h of omega. But what about the phase? We will plot it in the next slide. But before going further to the phase, we have to first start to observe this graph, this h of omega. Okay, for 0 omega, or for 0 frequency, because as you remember, omega equals 2 pi f. So simply, if you divide this omega by 2 pi, you will get a frequency axis. So omega and f are correlated somehow. So for 0 frequency, you get 1. You will multiply the system by 1. Please remember that y of omega equals h of omega times x of omega. So the zero frequency component for x will be directly multiplied by 1 and we will pass directly. When the frequency of x starts to increase, this signal will now be multiplied with a value smaller than 1. So some sort of attenuation to the signal. As far as the frequency increase, this attenuation factor increase till it will be nearly 0. So what you are going to do now with the signal is, for low frequency component, this signal, the actual signal or the output is simply equal to the input. While you are increasing the frequency, this input is multiplied by a smaller number, so the output starts to decrease, and then it tends to be 0. So we call such a structure a low pass filter. What I mean by a low pass filter is that this structure simply pass the low frequency component and filter the higher component. So what this structure did is simply that for zero frequency, and this is relatively low frequency, it will somehow pass without a problem. And then whenever the frequency increases, this signal or this the output signal will tend to 0. It will not pass. So it only passes the low frequency component and it stops the high frequency component. So this is a very important filter. It's called the low pass filter. Let's now return back. Let's now return back to the other side of the equation, which is the angle of the angle of the h of omega. So h of omega, I'm sorry, not an absolute, h of omega equal 1 over RC times 1 over RC plus j omega. We now need to calculate the phase for h. The phase is simply tan minus 1, the imaginary part, over the real part. But what is somehow difficult here, my dear students, is that we don't have real, imaginary, real and imaginary part simply because real and imaginary are in the denominator, not in the numerator. So what we are going to do in a very simple manner is that we are going to multiply this signal, this h of omega, which is equals to 1 over RC times 1 over RC plus j omega. We are going to multiply it by its complex conjugate. So it will be very simple. 1 over RC minus j omega and 1 over RC minus j. When you are multiplying a complex function which with its complex conjugate, then the output will be pure real. So we are not interested in the output. And then this is simply, so all these functions will tend to be a complete real function. And then this is the imaginary. So the phase will be simply tan minus 1, the imaginary part, which is omega, over the real part, which is 1 over RC. Or in a more simple manner, the phi will be, here we have a minus sign, so tan minus 1 omega RC. This is a very simple, a minus sign here due to this minus. So this is tan minus 1 omega RC. This is the phase. As you can see, this function represents the phase. Actually, maybe we will not go deeply about the phase analysis we will just make it mathematical and make it do some plotting for it, but we will not go deeply for it. But we have to consider it because whenever you are plotting a complex function, you have to plot it in the form of a magnitude and phase. So let's now return back to the slide. Here you can see this is the real. The first is the real part as we already plotted, and it represents what's called a low pass filter. And again, this is the imaginary, or not sorry, not the imaginary. This is the phase part, which represents the 10 minus 1 minus 10 minus 1, which is the same as arctan omega r's. So this is very simple how we plot the a complex function, and we know now what's called the frequency domain or the frequency responsible for the signal. Now let me terminate part number 4 by this important conclusion related to that multiplication in the frequency domain is simply the convolution in the time domain. We already discussed this. In the next part, which will be inshallah the final part of this lecture, we are going to see this very interesting example where we have h of t and x of t, and we are now interested in finding the output signal y of t due to the convolution between h of t and x of t. This is the end for part number 4. See you inshallah in part number 5, which is the final part of this lecture, dealing with an important example related to the system analysis. And actually, we are going to conclude, or we are going to terminate this lecture with more and more investigation about the word filters. We have already shown what's called a low-pass filter and the frequency response for a low-pass filter, but there is also another type of filter that's also interesting for us. So we are going to do more and more investigation about other types of filters. Thank you very much, and see you in lecture or in part number 5.